So now we're going to look at a little bit of motion in a, let's just call it a predetermined animation. And the idea here is, well, we can use this in a lot of different graphical programs, but we're kind of looking at this in the application like in the third assignment. If you choose just an animation there, an application that runs without any user input. So it's a predetermined animation. Same things happen at the same time in the animation, regardless of on which computer we run it or how we run it or what input we put in, because it just runs the way it's supposed to run every time. And for an animation like this, we're kind of going to start looking at the time we use a little bit differently, in that we're not going to look at the delta time, which is the time that each frame takes, and then do incremental motions on the frame time. Instead, we're going to say we want to introduce a variable that we can call something like current time, and say this is the current time of the entire animation, the time since the program started running. So I want something to start happening after, say, 5 seconds have elapsed of my program, and I want that to happen until 10 seconds have elapsed, and then I want something else to happen. And I want to be able to calculate each frame from the current time. I don't want to have to increment up to the current point. I want to be able each frame to calculate it based on the current time, regardless of what happened before. So the first thing we're going to look at here is a simple linear motion, and after that we're going to look at motion along a Bezier smooth curve, a Bezier curve. Bezier curves can be used for many different things other than motion along them, making Bezier patches and making actual surfaces, smooth surfaces. But for now we're going to look at this application and kind of explain it in terms of this motion idea. But to begin with, let's imagine that we have a point and another point here, and we'll call this point here P1, and we're going to say I'm going to imagine that I have some start time of my animation. So I have some start time, and at the start time I want the position of something, whether it's the camera or some object. I want the position of that to be P1. So at start time I'm at P1. Then I have this point here P2, and I want to be there at the end time of my animation. So for now let's not put any values in there, but my idea now is that I start moving from here at start time, then I move in the linear motion until end time, and at end time I end at exactly P2. So I want some way to calculate this, and we can imagine any values for this. We can imagine that start time equals 5 seconds. So after 5 seconds have elapsed, I want to be here, and then when 10 seconds have elapsed, I want to be here. So for the duration of 5 seconds, I want to be moving in a linear motion from P1 to P2. And we can say we have some point P, which equals P1 when current time equals start time. Same thing here, P equals P2 when current time equals end time. So what we want to do now is to set up a simple formula or a simple method to get the current position, the point P, for any current time. Not just exactly. We could say if current time equals 5, then P equals P1, and if it equals 10, then P equals P2. So we get the endpoints, but we want something that gives us this linear motion here. So we can imagine that we have somewhere here current time equals 7. So P equals what at this time, at this point? We imagine that it would be positioned somewhere around here, kind of not basically 2/5 of the way from P1 to P2. But we need a way to calculate this for any given time, any given current time. So the first thing that we want to do is to basically be able to set up some kind of parameter which we want to be 0. So I'm going to set up this parameter t and say I want t to equal 0. I want this to be a lowercase t to equal 0 when current time equals start time, and I want t to equal 1 when current time equals end time. So now I want to go in here and say if current time equals 7, then this parameter t equals what? So what we basically need to set up here is a way to say, how can I take the time using current time and start time to get something that equals 0 when current time equals start time. So we can say any number minus itself would give us 0, and as current time rises it gets bigger than start time, and we want positive numbers here. So imagine that current time minus start time, so we can start with that and say t equals current time minus start time. Okay, so that'll be above the line here. However, now we would get, if it's only this, we'd get 0 at P1 here. T equals 0, that's good. But at current time equals end time, in the case where start time is 5 and end time is 10, at the time 10 we'd get 5 from this. Current time minus start time, when current time equals end time, would be 5. So we need to have some way of making sure that we get 1 here, and any number divided by itself gives us 1. So when current time equals end time, then current time minus start time equals basically the duration from the point in time when we're here until the point in time when we're here, which is basically end time minus start time. So at the point when current time and end time are equal, and we can say end time minus start time equals current time minus start time. So when the denominator here equals the numerator, we get 1, but when current time equals start time at the beginning, we get 0 in the numerator and thus 0 in the whole number. So this here is our parameter. And so we should be able to go in here and say, well, t equals current time minus start time. We can put this in a better spot here. Well, you can also just move this entire thing, I think. See if that works. Move this a little bit out of the way and say t equals current time minus start time divided by end time minus start time. Okay, so now we have our parameter, and this parameter helps us a lot in that we simply have a way, whenever we have some kind of time interval that we want something to happen in, and we have either a linear function or a curve function, it's very nice to be able to say the beginning begins at 0 and the end is at 1, and then everything in between is some kind of weighted average between the points, in this case, or the control points, a weighted average, or what we call a linear interpolation. And a linear interpolation is easy to take when you have a parameter that starts at 0 and ends at 1, basically giving us a weighted average. So what we're going to do now is, this is the parameter t. What we're going to do with p here, we're going to say p equals the linear interpolation, or lerp, of p1, p2, and the parameter t. And if we move just a little bit down here and say, oops, just a little bit lower here, and look at the linear interpolation in more detail, you can say the linear interpolation between a, b, and some parameter t. And a and b can be anything. They can be numbers, they can be points, they can be vectors. Linear interpolation between these two entities and t is basically a weighted average, where t is how far away from a in the direction of b we are. And it will in the end be 1 minus t times a plus t times b. And if we look at this, we can see that 1 minus t will give us 1 when t is 0. So at the beginning, when t is 0, 1 minus t is 1, so we get a out of this equation, or out of this formula here. In the end, when t equals 1, when we're 100% of the way from a to b, 1 minus t will give us 0, whereas t will give us 1. And of course, in the beginning, 1 minus t gives us 1 and t gives us 0. So we have full A, 0b. In the end, we have 0a, full b. In between, we have a weighted average. So in this motion example here, if t equals the current time minus start time, that's 0 at the beginning, divided by end time minus start time, so the whole thing is 1 at the end. We could take a weighted average between the points using this parameter, using this formula for the linear interpolation, and that will give us a motion which starts here at the time 0 and ends here at the time 1, or at the parameter 1. In this case starts at start time, ends at end time, and we'll look at putting this into a program just when we've finished looking at these explanations a little bit. So this is a basic linear interpolation, and a basic idea of taking this start time, end time thing, calculating the parameter from that, which is 0 at start time and 1 at end time, and then applying that into some formula for a motion. In this case, a linear formula for a motion between 2 points. What we want to look at now is just a little bit of a more interesting motion. So let's imagine that we want to be able to not only move linearly between 2 points, but have a few control points that dictate our entire motion. So what I'm going to do is I'm going to draw points here. Point 1, point 2, point 3, and point 4. Let's just look at this with 4 control points here. And what we want to happen, or what a Bezier function is going to look like in the end, is something like a curve going from P1, being pulled by P2 and P3, and ending at P4. And the way we calculate this is that we're going to say at 0, we start at P1. Let's imagine that we go into this at some time where we have a t that equals something in between 0 and 1. We can draw it as if we have a t that equals 0.3. So we're 30% along this way. And so what we do is we imagine the linear motion between here and here, between P1. We can label these points here. P1, P2, P3, and P4. So we imagine the linear motion between P1 and P2. And we're going to say the linear interpolation of P1 and P2 using the parameter t equals 0.3 is somewhere around here. So we can say this here, we can call it P12, and it equals the linear interpolation of P1, P2, and the parameter t. Okay. Then we imagine that we have a linear interpolation going here between P2 and P3. We're going to say this point here is something we can call P23, and it equals the linear interpolation between P2, P3, and the same parameter. Then imagine that we have a linear interpolation between here, so somewhere around here we have the point that we can call P34, which equals the linear interpolation between P3, P4, and the same parameter again. So now we have 3 points. And now the idea behind the Bezier function starts, because now we can imagine this as a recursive function. So we had a list of 4 points. These points were P1, P2, P3, P4. Using those, we've now built another list with 3 points, P12, P23, and P34. These 3 points are now a new list of points, one shorter than the original list, and we can call the same function using those 3 points. If we were to implement this recursively, we would now just call the same function we're working in, except with a list of 3 points. That would then make a list of 2 points. Calling that again would make a list of 1 point. So each time we call it, it makes a list that's one shorter. And finally, when we only have 1 point left, we return that point. And that is the actual Bezier function of the parameter t. So if we look at this letter here, we have this point here, 30% of the way between P12 and P23. And we have this point here. So you can imagine this point, you call it P1223, equals the linear interpolation between P12 and P23, and again the same parameter. We're not changing the parameter here. Here we have point P2334, which equals the linear interpolation between P23, P34, and the same parameter t. So recursion again, and we get the linear interpolation between these 2 points, again, about 30% of the way along that, and we can call this the point P. So P12232334, or in this case, since we only have 4 control points, this is the final point. This is our point P, and it equals the linear interpolation of P1223, P2334, and the same parameter t. Now we only have 1 point, and this here, in this case, is the value that the Bezier function gives us with these 4 control points and the parameter t. Now, if we were to write this entire thing up, we could now say P equals the linear interpolation between this equals the linear interpolation between these, which are the linear interpolation between these, the linear interpolation between P1, P2, and T, and the linear interpolation between P2, P3, and T, this and T. Close that linear interpolation. Can go on and just finish writing this out. Interpolation of this and another equally big linear interpolation here, except we have to say this is P2, P3, P3, P4. So we have the linear interpolation between P1, P2, and T, linear interpolation between P2, P3, and T, again the linear interpolation between P2, P3, and T, and the linear interpolation between P3, P4, and T, this inside a linear interpolation on T, this as well, and then finally closing this. So this is the entire function, which incidentally equals, let's say p equals, this would be 1 minus t times something plus t times something. And this something here would be 1 minus t times something plus t times something. And this something here would be 1 minus t times p1 plus t times p2. This something here would be 1 minus t times 2 plus t times p3. This something here would be 1 minus t times something plus t times something. Something here would be 1 minus t times p2 plus t times p3, and this something here would be 1 minus t times p3 plus t times p4. So now if we simplify this, we can finally say for p1 it's only here, so we have 1 minus t times 1 minus t times 1 minus t, which gives us 1 minus t one minus 2 to the power of 3 times p1 plus, then we have p2 here, which is 1 minus t times 1 minus t times t. Again here, 1 minus t times 1 minus t. And again here, 1 minus t, 1 minus t, t. So we have 3 times 1 minus t to the power of 2 times t times p2. Almost the same thing for p3, except here we have t to the power of 2. And finally we have t to the power of 3 times p4. So 1 minus t to the power of 3 times p1, t to the power of 3 times p4. So we can see that when t is 0, 1 minus t will be 1, t will be 0, meaning that everything else has a t in it, giving it 0, so we'll have full p1, just 1 times p1. When t is exactly 1, this will be 1, 1 minus t will be 0, so we'll have 0 in everything except p4. So we're going to end up at p4 at t equals 1. In between, all of these will kind of be pulling at it. So this is the point at 0.3, and we can see if we kind of move all these lines along, if we were to set up, like raise this number to 0.4, this point would be somewhere around here, this point somewhere around here, this point somewhere around here, meaning this line between here would be like this, point somewhere around here, a point somewhere around here, finally here. So we're moving kind of like moving along these tangents like this. So this is what the final curve looks like, more or less. And what we have here, right? What we have here, basically in this bottom line here, this line here, is simply a way to calculate where we are along this curve when the parameter is exactly t. So any t between 0 and 1 will give us some point along this curve. And if we move this along into a program, let's say, and we increment this by the frame time, so the current time is rising all the time, somewhere between start time and end time, we will each frame get some point, but since we're running the frames constantly, we'll get an animation and it'll move along this curve smoothly. We'll look at that in just a minute in the program. But here's basically the formula for a Bezier curve with 4 control points. If we were to do the same with 3 control points, we would be able to say something like P equals 1 minus T to the power of 2 times P1 plus 2 times 1 minus T times T times P2 plus T to the power of 2 times P3. So 3 control points, this would be the formula. Because we're simply doing the same thing, except we only have 3 control points, so it's basically taking this same thing except between these points, P1, 2, P2, P3, and P3, 4. And we could set up these formulas for any number of control points, but when we're above 4 control points, we can just use a recursive function. But usually we wouldn't use Bezier curves above 4 control points. Instead, we'd kind of splice together many Bezier curves because we have so little local control. The only points that the curve actually goes through are the first and the last point, whereas the other ones just pull. So the more points we put in between, the less effect each one will have. So we'd rather just build, simply build or splice together, build kind of sets of different 4 control point Bezier curves. And just quickly, I want to look at, let's just draw this a little bit up again. I want to look at the idea if we have P1, P2, P3, and P4 here. P1, P2, P3, and P4. If we want these curves to kind of be spliced together nicely so that the speed and direction along them is continuous when we go up. So we can imagine if we start another Bezier curve, started here, obviously the first point has to be the same one, the next point is here, you get a curve that goes like this, and then suddenly it starts going in a different direction, and we have a kink in our curve here. If we want this to be a nice continuous curve that continues down here, we kind of have to calculate the speed and direction along it. And the thing is, we can take the derived function of a Bezier function, so the derived function of the Bezier curve with 4 control points is in fact a Bezier curve with 3 control points. And the control points are the differences between these control points, which in fact are vectors and not points. So if we say, make the vector v1 here, we make another vector v2 here, we make the vector v3 here, and we can say P1 equals P2 minus P1. I want this to be a lowercase v. P2 equals P3 minus P2, and P3 equals P4 minus P3. We can then say the Bezier function for the speed vector along the curve, the speed at which we're traveling based on this vector t, this parameter t that we have, is in fact this formula here. We can just steal that here, except we're going to say speed vector v. So we have v1, v2, and v3. The main thing we can get out of this is, yes, we can get the speed at any point, and we can actually use this to get this vector If we're doing a Bezier patch, we can use this and a vector on another Bezier curve and the cross product between them to get the normal onto the Bezier patch. We'll look at that hopefully in a program in a lab class later on. But that's fairly advanced stuff. But the main thing we get here is the speed at the beginning and at the end of the Bezier curve. So we can see that when t equals 0, 1 minus t equals 1, and we get only v1. So at the beginning, we are located at p1, and we are at the speed v1. At the end, t equals 1, everything else is 0, so we're only using v3. So at the end, we're located at p4, and we're traveling along v3. So using this, the end of one curve and the beginning of the next curve, we can now say, if I simply build the next curve where I make sure that, let's just call the next curve, say it has the points R1, R2, R3, and R4, I can simply say R1 equals P4. So the first point here equals the last point in the one before. Also, just going to add V3 here. So here we have R2 equals R1 or P4, it's the same one, R1 plus V3. And if we haven't calculated V3 necessarily, we can say the same thing. R2 equals R1 plus P4 minus P3. So basically, we take the difference between the last 2 points in the previous curve and make that the same difference between the first two in this curve, as well as making the first point the same as the last point here. Then we're going to get a nice continuous motion throughout. So starting here, going on here, getting a nice continuous motion to somewhere. Let's imagine we have a point here and a point here. So what we can now do is we can build a full function that can take any number of points and splice them together in this way, saying the first 4 points are the first 4 points, or build the first Bezier curve. After that, we take 2 and 2 points together. Not this point, but this point will be the 5th point in this list. This one will be the 6th. These two we calculate. So we say, read these 4 from a list. From then on, we calculate the first 2 here because we want them to just work out there. This one will be the same. This one here will be the same. This one here will be calculated using the vector. Then we take the next 2 points, and with these calculated points, we have the control points for the next Bezier curve. When we've finished with that Bezier curve, you can say the next Bezier curve after that, we might have some 2 more control points here, and 2 more control points here. We say this will be the first point in the next Bezier curve, then we'll calculate the next point, and then we take this point and this point. So our curve will be something like this, ending in this point. Take these 2 points now, this one and this one, except this will be the first point, the last point here, will be the first point in the next curve. Then we take the vector and calculate this point, which will be P2 in that Bezier curve, and this one and this one will be P3 and P4. Meaning we're traveling in the same direction, and we end up right here. So that's the way to build what's called a B-spline. So a B-spline curve is built like this. We use the formula for 4 control point Bezier curves, but only for the first one we actually use 4 control points. After that, we calculate the first 2, use the next 2 on the list. Calculate the first 2, use the next 2 on the list. So we take 2 and 2 points together, use them as control points from the list, but calculate for each curve. We calculate P1 and P2, from the last P3 and P4, then take P3 and P4 from the list. We calculate P1 and P2 and take P3 and P4 from the list, so on and so forth. And you can see how this here always gives us kind of a tangent to the curve. So we have much more local control now. We'll be actually passing through every other point, not just pulled by it, but actually passing through every other point. The other points which we don't pass through, they both pull, and they also determine this tangent here, knowing in which direction we'll be traveling at each point in the B-spline. So that's one way of putting together different Bezier curves. And if you don't actually build a B-spline function like this, you can still use this knowledge to take a couple of Bezier curves and put them together in a way where they will fit together, both in continuous in speed and continuous in position. So on to Bezier patches and more complex stuff. We'll do that later on, but for now I think we should just move on to the code a little bit and see how this actually looks in a program, moving an object along this curve. I expect you will want to move your camera along a curve like this in the project yourselves, but I think moving an object would be a nice test to do this. So let's go on into Eclipse now and see this in a program. Okay, so let's see if we can add a little motion to our program. What I'm going to do is I'm basically going to build like a separate motion class. Start with just a motion that does a linear interpolation, and then I'm just going to have a function on that so I can ask the motion, give me the position at this particular time. So I'm going to give this motion a start time, I'm going to give it an end time, and the control points that it should use to move along any curve or line. And then I'm going to set a function in it where we can say, if this is the current time, where should we be? So then you can take that motion class and you can make a list of those motion class and add it to some class for a moving object. And then say that object or this list of motions will be able to kind of sort itself on start times and always take the next motion and say, this is the motion I'm using now. Once the end time of that is reached, it'll simply fetch the next motion out of the list, and so on and so forth. So let's just start by building a little motion class here. Graphics, shapes. I don't know, should we build a new package maybe? New package. Just call it motion. Maybe graphics. That's nice. Okay, and we'll stick a class in here. Why is it on this side? Doesn't make any sense. Class. Let's just call it, I don't know, linear motion, or yeah, linear motion. Okay, so if we're now just going to make a motion class that has two control points, we're going to imagine that this is a Bezier curve with two control points, or just a linear interpolation. What do we need here? There should be point 3D here. D2. All right. Okay, what more do we need?
Time.
Time? Which time do we need?
Current.
We'll need the current time to be polled for where we should be now, but that wouldn't be a class variable. That would be a parameter. Yeah, we need start time and end time. Okay. No, it doesn't matter if these are private or public. Let's see in the end whether we need to set them. Let's just public linear motion, point 3D, 1, 2, not time start time, end time. Okay, so this should be all we need. We can say this dot p1 equals p1. Start time equals start time. Alright, like so. Okay, so now we have a way to build this with some points and some start time and end time. Now we want a function that we can simply say, this will, what do you feel better with? Should it return a point, or should I put a point in as a parameter and then it fills it in, so that we don't waste more memory, so we don't constantly throw things around. We could have this return a point, but I'm gonna do it like this and say get, let's just make this everything very clear, get current position, so float current time, and then we'll have point 3D, just call it out position. Remember that this is what we're going to be filling in there. So then we can take the position of any object that we have and simply send that in, have it filled in, and we'll be affecting the positions directly. Okay. So what do I do now? How do we want the functionality of this to be to begin with? What do we want to happen if we're not within the time between start time and end time? Do we want it to return, can't really return null. We can just say that it will fill in the position for P1 until start time end comes, and then it'll start moving, and then it'll send the position for P2. So how can I set that up? If time is less than start time, out position x equals start time dot x, start position, sorry, yeah, P1, that's right, P1. Alright, same for y and z. You can decide, we could also have a function in the point class where we can make this simpler, so I don't need 3 lines of code for this. But for now, it doesn't matter, just that it works. Else if current time is bigger than end time, do the same thing except for P2. I'm going to close that window now. It's worse than having the bird. Okay, so now we basically told it that if we're outside of this frame, we'll just give it the end times. We'll just give it the extremes. Fine. Finally, what do we do in the main case, if current time is actually between start time and end time? Any good ideas? Yeah, we're going to do the linear interpolation. We need to calculate the actual t for the linear interpolation first. I think it's simpler to do it first. So float t equals, what was that again? Current time minus start time divided by start time. Okay, now we have our parameter, and we basically have to say out position dot x equals 1
minus t times p1.x plus t times p2.x, right? Okay, so that would be our linear interpolation. Again, we could set up a nice function for the linear interpolation separately. Okay, so this should do something. We have a start time and an end time, and it simply gives us back where we should be based on some current time. So if we go to our game class now, we have some model here. Let's just throw in the motion here as well. It was called linear motion. And we could probably make an interface for motion that has these functions, and then we can just build each one differently. And then we can make a list of motions that has linear motion sometimes and Bezier motion sometimes and things like that. For now, linear motion, let's call it motion. Where was I writing? Motion here. Motion equals new linear motion. Okay, where do you want to start? -1, -1, -1, and 1, 1, 1 will be the answer. Okay, let's say start time is 2.0 and end time is starts at 2 seconds and then moves for 3 seconds or something. End time is 5. Okay, the question now is, where do we get this current time? So I have this linear motion. That's nice. And so now I want to be able, in my update function somewhere, just at the back of the update function, we'll say model dot, okay, the model doesn't even have a position. The model is just the model itself. So we're going to need an actual position here. So we'll call it motion, and then we'll say point 3D model position. And let's just say model position equals new point 3D, and we don't care where it is. It'll probably just be at 0, 0, 0 now. But every update, we want to say model position. No, we do it the other way around. We say motion dot get current position for some current time and our model position. So my question is, where do we get this current time? I'm going to imagine that it has to be a class variable here. We'll just go ahead here and say float current time. But how do I get this? So get delta time gives me the time between frames. So should I just add that up? Okay, that's one way. Every single frame to take get delta time and add that up. So we can say I'm going to add one more thing so that the first frame we start at 0. So we don't start by adding something, especially if the program takes a while to load. We don't want to already be a few seconds in. So I want to make sure that we start here, we have current time, and let's just make a boolean here. Call it first frame. Say it equals true at the beginning. So then I can go in here and say if first frame, I'm going to say current time equals 0 and first frame equals false. Okay, and in any other case, we'll do current time. Okay, this is one way of doing this. Current time plus equals either delta time, or we can actually use GDS X graphics dot get raw delta time, I think it's called. Doesn't matter, there's a bit of smoothing in the regular delta time function. Okay, this is one way. We could also just say in the beginning, or if first frame, we could say we could build like an offset. We could use the system dot current time millis. And we could say in the beginning we set some offset to this, and then in every other frame we say current time equals current time millis minus the offset. But then we have to work that into seconds as well. You can just experiment with that. I don't know if we're going to get like if the time is going to be either a little bit off or if these, because this is an incremental change again, it might not always be exact, but I think it's exact enough for us to never notice. So current time plus equals this. So now rather than always getting this short amount of time, which we can just multiply with, we have this full time from the beginning of our program. Plus equals. It's adding this to. It's the same as saying equals. Yeah, the current time is the time since the program started. Yeah. Raw delta time is still a delta time. It's just not smoothed between frames. Raw delta time is the actual true time that this particular frame took. But what libgdx does is it takes averages over frames and kind of smooths it out so you don't get jumps. But in most cases it doesn't matter which one you use. Either one will be good enough for us never to notice. Okay, so now we actually have some current time. Now we get the current position and put it into model position. And then we actually need to set that. So before we draw this model here, model.draw, we push the matrix here. Okay, we add this translation here, 0. Okay, it's already sent up by 2, so let's just take this translation out and instead put a translation. Okay, let's add a translation. Actually, the rotation should be below that then. Of model position, and you'd obviously do this kind of in some separate class, just keep track of this. Now I'm just doing this in my main code, just throwing around all these positions. It's not super clean code, but model position dot y and model position, oops again, model position dot z. Okay, so we add this translation. The question is, oh, we'll just see what happens. There it is. Now it starts moving and ends up there somewhere inside the pyramid. Okay, so this worked. Let's try different numbers here. New linear motion, let's start it at 4 in the y. We can just end it at 6 in y, and let's make it move a little bit faster. So there it is, and there it moves, and then it stops, and that's all that's happening. Okay, so not super interesting, but if you line a few of these up, it'll become that much more interesting. Now let's take this linear motion class here, just copy it, paste it back in here, and call it Bezier motion. So what we need in our Bezier motion is 4 control points, right? P4, P3, and P4. Start time and end time works exactly the same. We need points 3 and 4 here as well. This works the same. If current time is less than start time, we set it to P1, otherwise to P4. And finally, this needs to be a little bit more complicated. Yes, True. Thank you. 4 into the constructor, P3. Okay, so now we need to set this formula up here. So for P1, that'd be times this 3 times. Sorry, yeah, I'm not using the POW function. I'm just gonna do this way. Okay, so this times T times 3. Let's just copy this. So P4 just has T times T times T, T to the power of 3. P should be P3, right? Or did I take a wrong? Like so, plus 3 times this times T. Is this correct? P1x 3 times 1 minus T to the power of 2 times T, 3 times 1 times P3, and that times P4. I'm going to have to take the entire thing 3 times. If anyone has a quicker way of doing this, then feel free to let me know. And here, C and Y. Okay, so let's go into the game class again and say now this is supposed to be a new Bezier motion. So I probably have to import that. Okay, now we need more control points. Let's just cut this down here. So, okay, so start here, go up to here. Let's keep up there, but go somewhere really far away. Minus 4. And we just can come back down to 3 here. 1, 1. That's fine. Let's just see what happens. What is wrong now? Oh, yeah. Again, it would be nice to just have some parent interface here that we could. That was something. Then obviously you just have to get control of your own coordinate system. And so that's like that. If we simply change the start time and the end time, wait a little bit longer and then have the motion happen one more time. It moves up there, it goes in some kind of smooth curve right into that pyramid. So yeah, not super impressive here, but once you set this up and kind of add to it and work with it, you can get interesting results. Moving the camera along with that, moving the point that the camera is looking at along another Bezier curve, moving your objects along curves, and then also along lines. And especially for camera motion, this is can be really interesting. Moving the camera along one curve and moving the point that the camera looks at along another, and then just calling the look at function every frame using those points, and you can get interesting camera movements and transitions into that. So are there any questions or anything you want to see done in this program before we end this? All right. Class dismissed. Thanks.